have discussed enough about the philosophy of the multigrid approach. Let us try to increase our understanding by taking a very simple example and see how we go about the solution of this. So we will take our well known familiar example of Laplace equation, which we know is not irrelevant in the context of, for example, the solution for the pressure correction or the pressure equation approach, and we look at the one dimensional form of it, and then we can see how it can be extended to the two dimensional form. So we are looking at an equation like d square phi by dx square equal to some f. This is the equation, it is one dimensional. So we have an x domain going from 0 to capital L, which we break into so many control like that, and we can say that this is our point I here, and this is I plus 1, I minus 1, and I plus 1, and so on, and we can make use of central difference approximation for this and write a discretized form of this as phi I minus 1 minus 2 phi I plus phi I plus 1 by delta x square equal to fi, and we can convert this into a phi equal to b, incorporating the appropriate boundary conditions at x equal to 0 and x equal to L. So this is the linear algebraic system of equations that we want to solve using the multigrid approach. So let us say that we have run this for n number of iterations, using the Gauss-Seidel method. At the end of this we have a solution phi I n, where I covers all the points up to this. This is not necessarily the exact solution because there is some residual, and if you were to substitute this here, you would get phi I minus 1 n minus 2 phi n plus phi I plus 1 n, and this won't be exactly equal to f I plus some residual rho I n. Okay, so if the residual is 0, then we have the exact solution. So right now what we have is this equation, and the current solution phi I n at the end of n number of iterations using Gauss-Seidel method does not satisfy the governing equation exactly, the discretized equation exactly. It leaves the residual rho I n, and that rho I n is the residual at each point, at each node at the end of nth iteration. If you carry out another one iteration and then get a new solution at n plus 1, the residual will change. If you have a converging solution, the residual will decrease and decrease with increasing number of n, or the number of iterations. So if you were to now let us say that psi I phi tilde n is the exact solution of this equation, of the discretized equation. So then this means that we can say that phi I tilde I minus 1 minus 2 phi tilde I plus phi tilde I plus 1 is equal to fi divided by delta x square is equal to fi, and this is so that the exact solution obviously satisfies the governing equation. Now we can there is a 1 by delta x square here, so we can subtract this from this, and that will give us error at I minus, we can write it as phi I minus 1 tilde minus phi I minus 1 n minus 2 times phi I tilde minus phi I n plus phi I plus 1 tilde divided by delta x square is equal to this fi here cancels with this, and we have rho I n, and this is nothing but the error at the ith point. So this we can say is the error at I minus 1th point at nth iteration step, because this exact solution, this is a computed solution at the end of n iterations. So this is the error at this nodal value at this iteration step, and similarly this is minus 2 epsilon I n representing the error at this nodal value plus error at I plus 1 n divided by delta x square is minus rho I n. So this is the error at the end of n iterations using the Gauss-Seidel method, and what we are saying is that at the end of the first iteration or at the beginning there is some error. Okay, at the beginning you have phi I 0, this is the initial guess, and if you were to substitute this you would get rho I 0, that is the initial thing, and then you would have an error distribution at the 0th time step, and as a result of n number of computations on the error distribution using the Gauss-Seidel method, you have smoothened out some of the fine scale variations, and then you have come up with a smoother distribution of error as given by this at the end of n iterations. So now what we want to do is that we are claiming that this is smoother than the initial error distribution, and therefore, so whereas this variation can be like this variation for the same thing will be like that, and since this requires a small delta x here, the same thing will not be showing this much variation, and we will see that on the same delta x we have a smooth variation, where therefore we are saying that we do not need such a fine grid. It is sufficient to have maybe a grid like this, and using these reduced number of points also I can draw a smooth curve, whereas with this if I were to have grids like this I will not be able to show a variation of this particular thing. So at the end of n number of iterations a fine distribution high frequency distribution component of the error is reduced so as to give us to retain only a low frequency error distribution after n number of iterations of the discretized equation using a smoothing kind of method for the solution of a phi equal to b, like the Gauss-Seidel method or SIP method. Now what I want to do is that I do not want to do further elimination of the error. I ultimately, when I have the exact solution, the error will be 0 and it will not vary with space. Okay, I want to go down from here into this and then finally onto the 0 level, but the point that I would like to say is that because I have a smooth variation I can represent this using fewer number of points with increased grid spacing, and then continue further reduction on this smaller number of grid points and reach the end distribution where error at all points is very low and almost equal to 0. I want to reach that end point quickly, not by doing further computations on the small delta x but on a larger delta x. So what we want to do is that instead of working with further equations on this smaller grid, I want to replace this grid with a bigger grid, with a bigger delta x, so that if I take this value here, I drop out this. For example, I can have, for every alternate point I have this. So this is my capital I on the coarse grid, which corresponds to the small I here, and I plus 1, I minus 1 here on this corresponds to I minus 2, and this is I plus 1 here corresponds to I plus 2 here. So for every 2 points I have one grid spacing. So my delta x, delta capital X, is twice delta x, just as an example of a coarse grid. Now I want to do further error reduction on capital I grid, not on the small I grid. So it means that I have to have an error distribution represented like this, in terms of capital I minus 1 and capital I, A plus B plus C, error I plus 1 divided by delta x square equal to something. Okay. How do I derive this? If I am able to derive this equation, then I can work with this equation and reduce the error. In order to do this, I say that the error equation on this coarse grid for a point centered about this covers this domain, and this equation here covers the domain which goes from small I minus half to small I plus half, like this. So to this I need to add half of this domain and half of this domain to get to this. So I am saying that I here covers from is something like half of error I minus 1 plus the error equation at I plus half of. So I am roughly saying that this is the equivalence of this. This should give me the overall error value at this point. So in order to derive an error equation on the coarser grid, I write the error evolution equation at this point and at this point and this point, and then add them together with this weightage so as to get the overall error here. And so I take this, let us call this as 1, and equation 2 will be the same equation written at I minus 1. So that is so this is the error equation giving the residual at I minus 1, and similarly if you come to this point here, that will be epsilon I n minus 2 epsilon I plus 1 n plus epsilon I plus 2 n divided by delta x square is equal to rho I plus 1 n. So now I say that in order to get this one, I take half of 2 plus equation 1 plus half of equation 3, and what will that give me? The delta x square is the same, so I can say that this is half of epsilon I minus 2 n I can say that is 1 by delta x square minus epsilon I minus 1 n plus half of epsilon I n is what I am getting from this, and the original equation here will contribute epsilon I minus 1 n minus 2 epsilon I n plus epsilon I plus 1 n, and then again half of this plus half epsilon in minus I minus 1 n I plus 1 n plus half of epsilon I plus 2 n. This whole thing is equal to half of rho I minus 1 n plus rho I n. Okay, we have minus here. So I have written whatever the error equation I have at point I and at point I minus 1, this is this one, and at point I plus 1, and I have added them together to cover a domain which is equal to the total domain corresponding to capital I in the coarse grid. Now can I do any simplification of this? I have minus I minus 1 epsilon I minus 1 here and this, so this will cancel out, and I have I plus 1 here and minus of I plus 1, so this will cancel out and I have plus half of this and plus a half of this, and this is minus 2. So I can write this as, I can now take out half epsilon I minus 2 n is what I have here, and here I have 1 is left, and then I have this one, so I can cancel out the halves here and then get the following expression, minus 2 epsilon I n plus epsilon I plus 2 n divided by delta x square is equal to rho I minus 1 n hopefully there is no mistake. Okay, and what we now see here is this I minus 2 here, this is I minus 1, this is I minus 2 here, and this is I plus 1, this is I plus 2 here. So this point corresponds to capital I plus 1, this point here corresponds to capital I minus 1, this point here corresponds to epsilon I. So I can write this as epsilon I minus 1 n minus 2 epsilon capital I n plus epsilon I plus 1 n divided by delta x square is equal to rho I minus 1 n plus 2 rho I n plus rho I plus 1 n. These are all in terms of small i's, which I can call as rho capital I n. So now I have got an equation for the error evolution on the coarse grid, which can be written as rho capital I, where rho capital I is given as rho I minus 1 n plus 2 rho I n plus this, and this is the equation which is now written for spacing of delta x, and this is what I am going to solve for m number of steps iterations using Gauss-Seidel method. So at the end of this I will have epsilon I at n plus m, okay, at the end of n iterations carried out on the fine grid and m iterations carried out on the coarse grid. And because I have carried out m iterations on a coarse grid, the error would have reduced using because I am using a Gauss-Seidel method and it is a convergent method and so on. So the error would have reduced, and error would have reduced at a faster rate because this is a coarse grid. And secondly, it would have taken me far lesser number of mathematical operations to reduce the error from at the end of n iterations to at the end of this, because I am working with fewer number of grids, therefore the computational effort is less. So to come back to this, I reduce my error at the initial step using n number of iterations to error at epsilon in, and then m number of iterations on the coarse grid. So this is done on the fine grid, and then I have an error distribution here, and using this I estimate the error on the fine grid at the end of n plus 1 m, okay. And now I can say that I have an estimate for error, then I can say the roughly from this I can say the value of the function at I at the end of n plus some iterations is phi in, the value that I had here at the end of this things, okay, minus the error. Okay, so this is now, if I have this, then using this value I can go back to my original equation and then reduce the error for some more time on this, reduce the error in phi directly, and then I can come back onto the coarse grid. So essentially what we are trying to do is that from the original discretized equation we deduce the residual at the end of n iterations at on each of the fine grid points, and using this residual at each of the fine grid points we find out the error evolution equation on the coarse grid, and with this we work for further m number of iterations and then reduce the error to some extent. Now from this, so now we have error at so this we have error at I, error at I minus 1 and so on. So in order to find the error on the coarse on the fine grid here, we do an interpolation of these two to get the error here. This error is brought here, the error between these two is used to compute the error here, and this error is given here. So by interpolation from the coarse grid we can get the error on the fine grid at the end of n plus m iterations, and we can say that error at the end of n plus 1 m iterations is less than the error at the end of n iterations, because this is a Gauss-Seidel method and it is a convergent thing, and we have probably gotten into that asymptotic convergence kind of thing. So we have carried out some reduction of error by doing m number of computations on the coarse grid, and then once we have this error we can get a revised estimate for the phi value and then go back into this equation, and then we can do further calculations. Okay, so to summarize here, at the end of this we have the error at each of the coarse grid points. From this we get the error at each of the fine grid points by interpolation. And from this we estimate the value of phi I here in this way. This is already computed and this is the error, therefore we get the thing, and then we start again computations on the so this is the equation that we have. Now we start this with an initial guess of phi I n plus 1. And then we carry out another n number of iterations to get phi I at n plus m plus m number. Okay. So from this thing we get an equation for the error on the fine grid like this. Okay. So essentially we compute the residual at the end of n plus m plus n number of iterations. Using this residual on the coarse grid, on the fine grid, we evaluate the residual on the coarse grid without doing any further iterative calculations, and doing further m iterations on the coarse grid we get error distribution on the coarse grid at the end of n plus m plus n plus m iterations. So by interpolation we bring it down to error on the fine grid at the end of n plus m plus m, and from this we go back, we get the estimated value of phi I at n plus m plus n plus m. Using this as the initial guess we go back to this. So we are doing looping, starting with an initial guess, we get after n number of iterations we get a residual on the fine grid, and from this residual we in a way we compute the residual on the coarse grid, and using this residual on the coarse grid we try to minimize the error, to reduce the error on the coarse grid using m number of iterations. Using this error on the coarse grid we by interpolation we get the error on the fine grid, and using this fine grid we update the value of the phi that we have computed, and using this like this we can go through. So if you look at the so called error as a function of k, the number of iterations, you have, this is the initial error, let us say like this, part of this is reduced on k iterations carried out on the ith grid, and then we have another m iterations in which the error reduces on the coarse grid, and then it reduces another n m n like this on the fine grid, coarse grid, m number of iterations like this. So part of this error reduction is done on the fine grid and part of it on the coarse grid, again fine grid, coarse grid like this. This reduction is done by solving a phi equal to f. This reduction is carried out by solving a error equal to residual rho. Okay, so this again this is done using a phi equal to f, and this is using a epsilon equal to rho. So from this we estimate the error, and then we get from here error at the end of n plus m iterations on the coarse grid. So this we give as the input to get phi I n plus m, which will be the initial guess for this, and then we carry out further number of things to reduce this. So the computations done on the coarse grid serve as refinement of the initial guess for computations done on the fine grid. So this is how that the error reduction takes place on the multigrid approach. Part of it is on the fine grid and part of it on the coarse grid. What is done on the fine grid is the solution for phi. What is done on the coarse grid is solution for the error. Okay, so this error is used to guesstimate the value of phi for the fine grid calculations. So, and if you look at the computational effort, okay, so during the same n number of iterations m like this, the computational effort for this will be high and the computational effort for this part will be low, again high here, low here. So the overall computational effort, this is so low that it probably won't count, and so in carrying out this n plus m plus n plus m iterations, the computational effort is not fully at this level, it is only part of the time at this level and rest of the time it is at a low level. So the overall computational effort to carry out 2n plus 2m number of iterations is significantly less than the computational effort required to carry out the full solution, that is the whole number of iterations on the same fine grid. So in an actual case, instead of doing so many iterations on this and so few iterations on this, you may actually do it like this. So we can put it this as some residual reduction. So you may have the same effort. You have for a short time you are working on fine grid, and then you work for a longer time on this, and then again short time on this, and then longer time on this, short time on this, longer time on this. And in the process the residual is decreasing something like this here, and then like this, and so on a log plot it will be better, but you can see that some of the residual is being reduced during this time and some more is being reduced this time and some more here and so on, so that the residual reduction is carried out part of the time on the fine grid with high computational effort and part of the time on this, so that the overall computational time to reduce the residual from one level to say 10 to the power minus 4 of the initial level will be a fraction of the, only part of that fraction is part of that overall computational effort is done on this. Therefore the overall computational effort, which is the area under this curve, is not this whole thing, which would be the effort that is required if we were to use a single grid, but it is only this much. Okay, so the area under this thing is much less than the area under this whole thing, and that is why the overall computational effort decreases. So this is with the 2 grid. You can have multi grids, you can go from this to even coarser grid where you have this one and then this one like this, and then you can even have even coarser grid corresponding to this. So on each of these, as you go from here to here and here to here, you are trying to take the residual here and defining an error equation with the residual corresponding to this, which is estimated from the residual computed here and so on. So only in the coarsest, in the finest grid you solve A phi equal to B, and in all subsequent grids you solve for the error in terms of the residual which is computed from the earlier things. So the solution in a multigrid approach, it uses different equations on different grids. On the finest grid is where you get the actual solution, and on the coarser grids you solve only for error in terms of the residuals which are already computed. So you go from there are certain interpolation and restriction operations that are done here, that is in order to, from the computed value of residual on the fine grid, you have to get the value of the residual at the coarse grid so that you can work with this. So there is some interpolation or extrapolation that is to be done there, and from here you get the error, and by interpolation you can get this. So the overall effort to get the solution is partly for the solution of A phi equal to B on the fine grid, partly for the solution of A epsilon equal to rho on the coarse grid, and partly for estimation of residual on the coarse grid, and partly for interpolation of error on the fine grid from this. So the overall computational effort is considered to be typically found to be a small fraction of the computational effort required if you were only working with the finest grid. So the area under this shaded thing is a small fraction of the total area, and that is the gain in computational effort that we are gaining in the multigrid approach. And if we are very systematic and go through lots of grids, then we can really achieve significant reductions in the overall computational effort. So this is the basic idea of the multigrid approach, which results in almost a linear scaling of the computational effort with respect to the getting the solution.